All right, welcome to the LPL Colloquium. Our speaker today is Carson Fuls, who's been with the Catalina Sky Survey since I think 2015 or so. And almost exactly a year ago, he decided to simultaneously become a graduate student and the director of the Catalina Sky Survey. So I'm sure that's been an interesting year with all of the other things you've had to do. And that's all I've got to start. So go ahead and tell us about what you do.
All right, Mike, good? Sounds good. All right, well, thank you so much for letting me give this talk because, I feel like a lot of folks in the survey, since we mostly work at night, don't get to make it to the lab as much. This is a great opportunity to share kind of the details about what we've been doing, not just the broad, oh, we found a lot of asteroids and move on. So before I really get into the talk, got to do a little bit of history. You can relax and enjoy the view of our nice starlit skies, and that's our 60-inch dome. Just put yourself up there on the mountain like one of our observers. And I'll talk a little bit about the history. Can't get away from it. Catalina Sky Survey started way back in 1998. So we've been running over 25 years. It was started back then by Steve Larson, Tim Spar, and Carl Hergenrother, and they wanted to use the Schmidt telescope that's up on Mount Bigelow to look for near-Earth objects. It wasn't being used at the time, and they thought, oh, it's got a wide field of view. Yeah, let's hop on that. And the rest is history, as they say. Since then, CSS has been just relentlessly innovating and expanding and improving our operations year over year over year. And before I get into the details of that process, of that work that we do, I really have to acknowledge the stuff that I'm going to be presenting today is really the culmination of lots of people's work over decades. So keep that in mind because it's a lot to cover. And also, we're still not finished. We still consider ourselves a work in progress. So a brief outline, I'll tell you why in just a second. I'm going to start talking about processes. How do we actually discover NEOs? What are the nuts and bolts of that process? We discover them with survey, and I'll go over a little bit of the strategy we use when we're planning observations for discovery, and also really in depth on the image processing side, because that's what interests me, and that's what I wanted to talk about. But also our follow-up operations, where we go after known asteroids and try to get more observations to improve their orbit. That is a very different strategy, and we really try to optimize that with a queue scheduling system that we developed in-house. And finally, this has just recently started a second chance image processing pipeline, but I'll get into details of that. The second part of my talk is going to be about the products of the survey. The main product being astrometry, or measurements of positions of objects in space. We're going to go over the numbers really quickly. They still astound me when I look at them. And also our image archive. We've been running since 1998, and I believe we have images all the way back until then that are available to the public, and especially people at the lab. Come by our office and check them out. So we'll talk about access to those and past, present, and future projects that make use of our data. The reason I broke it up like this is because I hope, at the end of this talk, or maybe sometime in the near future, you hear about one of these processes and you're like, I've been thinking about that. I have an idea, something you could try. Please, let's work on that together. The second part, the products, I hope you take away, oh, that's an interesting data set. I could use that for my project. That's the goal of this talk. Let's get into it. We'll start with the survey strategy. This telescope in the background is the 60-inch Mount Lemmon Survey Telescope. If I say G96, that means this telescope. G96 is the Minor Planet Center code for it. They give 3-letter number codes to everything. It's short and sweet. So 60-inch telescope, fairly large aperture. And this is our narrow and deep survey. It has a 5 square degree field of view, and we do the 4 30-second exposures on the sky to create a set of 4 images. That's what we look at. Detect 50 is one of our FITS keywords. That's basically, we look at all the known objects in the field and we chart how many of those per each magnitude bend we find. And when that number drops below 50%, that's our detect 50. So we detect 50% of 21.5 magnitude objects and brighter. So that's kind of telling you the limiting magnitude in an indirect way. Because of the field of view, this telescope can cover the entire visible night sky in about a lunar month, give or take, and that is highly dependent upon weather. You know, if we have a bunch of clouds during a particular lunation, we're not going to cover the entire sky. Our strategy with this telescope has been, we start at high declination bands and we do wide bands. And then we start dropping down. This is right after full moon we start observing. We start dropping down until the moon has moved a little bit off of opposition, and then we drop immediately to opposition. And we do a narrower but deeper in RA set of images right on opposition, because that is the optimal place to find new NEOs. And then we start back up and keep going down. I know that's a lot for us. I have an image to show that. So here's the northern deck bands. We'll do some of these. They're quite narrow in RA. We drop down, and then we do these wide opposition focus bands. And then we go back up and we try to get all of this in 1 month. Like I said, highly weather dependent. While we're here, y'all notice these big gaps on both sides? Any clue what that is? What is it?
Galaxy. Milky Way galaxy.
Yeah, that's right. That's the Milky Way. We don't observe through the Milky Way. The star density that there is too much for our image processing pipeline. Our other main full-time survey is our Schmidt telescope, 27-inch, 0.7 meter, very wide field of view, 20 square degree field of view on a single chip, no gaps. It's glorious. Here we do 4 14-second exposures. And our detect 50 is a lot brighter, 19.5-ish. This telescope with that field of view can cover the entire night sky in a night and a half, which is great. So we basically just observe the north, observe the south, observe the north, observe the south. And there's a lot of overlap right in the center, but right in the center is opposition. So that's great. Both 703 and G96, the 2 telescopes I showed you, use automated planning software. So when an observer gets to the telescope, they're going to use the software and say, hey, it's tonight, and I might have 20 additional fields that I would like to do something with, maybe follow up a known object that I know I'm going to have to do. What can I observe tonight? And our planner will generate one of those deck bands or an opposition focus plan, depending on what the observer tells them. So we're not picking individual points to observe in the sky. That is automated because it's a lot of work to do it the other way. And we don't have that much time. All right. This is an example of the sky coverage for our Schmidt, and you can see it just north, south, over and over. It's still productive to cover the same region, especially at opposition, because the Schmidt is really geared to discover very close, fast-moving objects. And so they enter and exit the region of detectability very quickly. So even a day later, they'll be refreshed. Our other part-time survey that we operate jointly with Spacewatch is the 90-inch Bach, or V00. So this is a very deep and very narrow survey. It has about 1 square degree field of view, which is really good. And we also do 4 30-second exposures for each region of the sky. But the detect 50 is 22.5. That's really dim. Like I said, this is a part-time survey. We get 6 to 9 nights per lunation. It's a competitively scheduled telescope, so it changes. And it has a very specific plan of survey. Early evening and morning, we are focused on an Earth Trojan search, right? So we're looking as close to the sun as we can right after it sets. But once that region has dropped below the horizon, we go right to opposition along the ecliptic. because that's where we're trying to find those distant objects that are undetectable by our other surveys. The reason we have such different strategies for these different telescopes is because we don't want one to try to take discoveries from the other. We want them to be complementary, not competitive. So we put a lot of thought into the survey strategies for each of them. Okay, that's our main survey. How do we turn those 4 images into asteroid discoveries, right? It's a process, but this is where the real work of Catalina Sky Survey has come in on working on this image detection processing pipeline. So start with the 4 images, and they're taken about, depending on the telescope, 4 to 6 or 7 minutes apart of the exact same region in the sky. We do all the normal image calibrations that you would in astronomy. We do the flat fielding and the bias subtraction and all that. Then we run this special image processor that we call flat sky. It's a type of high pass filter on the pixels themselves. And its job is to flatten out the background noise and try to tighten up the stars. We actually developed this when we were working with OREX when they were trying to do particle detection near Bennu. And it turns out it works so well that we put it into our own pipeline. A great example of collaboration between projects you wouldn't think work, but yeah. It dramatically improves the consistency of signal to noise across the image. And from our senior software engineer, this was one of the biggest improvements to our pipeline that we have ever made. Biggest single improvement. All right, so once we have our images nice, we're ready to start processing them. We use the Sextractor source identification package. That's kind of an older one, but there's not that many software packages that actually extract sources from images. So it's that or SAO Starfinder, and that's kind of about it. But when we run that, we get to tens to hundreds of thousands of individual sources per image, right? This is a field from our Schmidt. So this is 20 square degrees, and all those dots are not all the sources. Those are the sources that were identified with stars. So that's around 35,000 sources ID'd. The actual number of sources is, I think, twice as large as that for this particular image. And remember, we take 4 images. So that's a lot of points to start to consider. You see the magnitude of the computational problem trying to find things in these images. All right, so once we have our sources, we also need to do a plate model. We use SCAMP, another package by the same author. We do a photometric 0-point calibration. Currently, we're using Gaia DR2. We plan to upgrade that to DR3 in the near future. We hope that will slightly improve our astrometry, but still in the future plans. Then I like to think of the pipeline taking 2 paths. So we do 2 different types of processing on the images. The first one is an image subtraction. So if you take one image of a star field and you mathematically subtract another image of the same star field, in theory, the stars will subtract out to nothing, but any object that's in one image but not the other will leave a positive source in the subtracted image. That's the way it's supposed to work. It's a little more complicated than that, but this is just based on those 4 images. So we'll subtract the second one from the first one, the third one from the second one, and vice versa. We don't have a standard image that we use for subtraction. Anyway, this is kind of what that looks like. So these dark halos with bright centers are the stars that were subtracted. But you'll notice that this has no dark halo around it, but that's because that was something that changed between the images. And that's what I mean when I talk about transients. A transient is anything in the image that changed between the 2 images. That will come up a lot. There are highly advanced image processing or image subtraction techniques that take into account stellar PSFs across the field and do very beautiful subtractions. But the problem is they take a long time to do that. The Schmidt, the PSF across the field of a Schmidt camera is like a 7th order polynomial that you have to calculate every single time. And we need this process to complete in less than 10 minutes. Can't do it. So we have a fairly naive image subtraction routine, but it works. The other thing we do is we start working with those sources that we extracted from the images. So we do dynamical thresholding on all these sources because we want a consistent number of sources in each of those images. Think about this. If you set a threshold for brightness that you expect in every single image, what happens when a cloud comes over your last image? It makes it useless, right? If we let the thresholds that we're trying to set our values for in our source extraction float be dependent on the images themselves, we can do a better job. We can account for instrument problems. Maybe there was something that got bright and launched a bunch of hot pixels. Maybe there was a cloud, or maybe the scene's really, really good. If we fix those, we don't do as good a job. And it really does allow us to dig deeper into the noise. We found that over time. So with those sources that we've collected, we start to compare them. And any source that's in one image and the other image and the third image and the fourth image and doesn't change, that's a star. Throw it out, we don't care. Anything that changed brightness or is in one but not in the others, that's a transient that we're interested in because that could be a moving object. That could be an asteroid. So we collect all those together, and then we send them to a newer part of our image processing pipeline, AI transient classification. All right, so we still have the sources from our image subtraction. These are the sources that were extracted from the normal images. We do a 40 by 40 array. We do cutouts of those sources we've identified as transients. We put those through a CNN, convolutional neural network, and it classifies them into standard categories of types of detections we see over and over in our image data. Those are stellar, so something that's nice, round, looks like a star. Those are streaks, that's an object that was moving during the exposure, so a moving object. Those are great, we want to highlight those. And a spike is a star diffraction spike caused by the spiders that hold our camera. And those look like transients because they're kind of bouncing around, but we know they're not real. So we can de-weight those. Oops. So this is kind of what that looks like. We actually don't make images. We do it directly on the data array, so it's much faster. But these three columns are all streaks that were identified, high confidence. These are stellar sources identified with high confidence. And these are spikes identified with high confidence. And that helps us out because that lets us eliminate some of those transient sources that we don't care about and lets us consider more of the ones that we do. Moving on. We take those two pipeline processes and we combine them back together. All right. Then we do a step where we cross-reference any object that we think might be in that field, and we try to match the sources with known asteroids, known comets that are there, because we don't want to process those right now. But now we're to the fun part where we form a tracklet. A tracklet is a collection of transients that we think is actually the same object. It's just moved from frame to frame. Okay, so transient, something that changes. Tracklet is a collection of transients. This could probably be its own course. That's what was told to me from our software folks. But we don't just start excluding tracklets. We rank them. And there are thousands and thousands of possible tracklets in our data. What do we rank them by? Easy ones that you can think of, signal to noise of the third brightest point. Why the third? Well, because if we just do it by the fourth, the least bright point, maybe something happened to it. And we need at least 3 out of 4 detections to know that this is a real object. Curvature of points. We're looking for neos, and neos, giving our short cadence, should travel in a straight line. They should not curve unless they're just right about to impact. They have a little bit of curvature. Number of misses. Like I said, we can we can still make a detection with 3 out of the 4 points. Maybe a fourth one was on top of a star. Maybe there was a cloud that came over. But if there's just 3 and they look like 3 solid good points, we can still consider that. The speed, we have a speed limit cutoff because satellites are going really, really fast and we don't want to report satellites. Also, even if there is a real NEO that we see going 45 degrees per day across the sky, if it's unknown, it's probably like this small. We don't, that's fine. We are looking for the big ones. Magnitude spread, the difference in the magnitude between the two, between the 4 points, it should be fairly consistent. Does it appear in both image processing pipelines? That's a good plus. That means it's something real. And the AI classification result, there's a lot more. Trust me, the parameter file is huge. Anyways, once we have ranked all of these potential tracklets, now it's time to go to work. We have an observer on site at the telescope who's going to go through this ranked list. And they're not going to go through the 1,000 of them for each set of 4 images. They're going to look at the top 15 ranked tracklets, or they're going to look at the top 20 ranked tracklets, right? Given those numbers, observers typically go through about 4,000 candidates per night. We do this for 2 reasons. One of them is because it's nice to send in new discoveries in real time. Then we can go follow it up and confirm, or just confirm whether it's real or not. We don't lose objects by waiting until the next day and then sending them in, and the uncertainty in their position has grown beyond what we're capable of following up. But also, humans are really, really good at this task. If we wanted to automate this procedure fully, we would stop right here, right? And just set a threshold and say, if we are 99.99% confident this is real, just send it. It's probably real. But this is planetary defense. And we want to dig deeper into the noise, which a person allows us to do. And we also really need to avoid false detections being submitted as real objects. That will take resources away from real objects trying to confirm these false detections. So that's why we have someone in the seat. They can also go fix things if they go wrong. They can also dynamically adjust the survey plan in case the clouds are coming in from one direction. There's many benefits, and our pipeline is built specifically to include the step where a person actually reviews this. The other side, oh God, this is what it would look like if you were an observer for CSS. Here's all the fields. Here is the ranked list of tracklets, and you're just going to be looking at them and saying, yep, that's real. Send it in. No, that's not real. No, that's not real. You say no a lot more than you say yes. So for the lower ranked tracklets, in the top 20 ranked tracklets, we find 98% of the objects. That means that about 2% of objects are lower ranked in that list of tracklets. We try to account for that by sending the next 20 to our citizen science project, the Daily Minor Planet. So I've talked about that in other talks. It's a great project. If you want to discover your own asteroids in your free time, go check it out. It's a Zooniverse-based project. Lots of fun. We just found our 3rd NEO. All right. That's it for survey and the image processing step. I know it's a lot, but that really is the magic. The secret sauce of CSS is that image detection pipeline that we've been working on for decades. We don't just do survey for new discoveries, though. We also do follow-up. That's because just discovering an object, just having 4 astrometric detections of it is not enough to establish its orbit. It needs repeated observations over a period of time to get a real handle on its orbit. So that requires more telescope time. Long time ago, when we just had the surveys, a decent part of the night, the survey would have to go back and re-observe objects they found that night and on previous nights. And that is a waste of time for a survey telescope. So we started a dedicated follow-up telescope that's right next to the 60-inch telescope. It's a 40-inch telescope. Get there in a second. We use the same image processing pipeline because it works just the same. There's one slight difference in methodology, though. Since we know about where these objects are and their rate of motion, we can track non-sidereally. So we can track on their motion and not the motion of the stars. And this helps build up more signal from that object, right? But, oops, do we only follow up CSS discoveries? We could, but we would be wanting for more targets. We don't find quite enough in a night to fully dedicate a follow-up telescope for that. And also, there may be other discoveries that are more important from a planetary defense perspective than following up our discoveries. And we're part of a greater community. So we don't just follow up our own objects, we'll follow up any object that merits it. But how do we decide what to observe? There's 36,000 NEOs now. Which one should we observe? I've also talked about that in a previous talk. We use NeoFixer. It's a targeting broker, and it looks like this. It's a giant web page. It basically ranks all known NEOs and new discoveries. See, these are temporary designations. They're not confirmed objects yet. It ranks them by planetary defense concerns. What does that mean? We care about how big the object is, how close it comes to Earth, but we also care about things like how uncertain is this object's orbit? If we know it very well, it probably doesn't need follow-up. If we know it not very well, it might need follow-up. We also look at the rate of change of its on-sky uncertainty. If it's becoming more uncertain very fast, we really need to observe that. We use this tool, and we've made this tool available to the general public because a lot of people around the world do the same type of work, follow-up of NEOs. And it's helped us out tremendously, right? That was a different talk. Not going to go into deep detail about NeoFixer, but it's helped out tremendously in our target selection and also on the efficiency of deciding which object should we observe right now. Another part of our follow-up workflow that's really great is our queue. We also use a queue for survey, but it really makes a difference when we're doing follow-up. Survey, you know, we're just kind of moving at a regular rate across the sky. The telescope's not moving very much. Follow-up here, 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 oh, back here, 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 all over the sky. That's not efficient, right? Follow-up targets can be anywhere. They each require different exposure times, different cadence. That's the amount of time between each exposure, so the object actually moves enough that we can detect it. They're all different. Having a human try to figure that out for each object, very inefficient. So we set up the queue to do that for us. It considers stuff like slew time of the telescope, how fast can you move your telescope, the rise and set time of individual targets. We better observe it after it rises, but before it sets. The exposure time required and the cadence. But our queue also needs the ability to change on the fly. As new objects are discovered, they may be more important than what your next target would have been. So we have to be able to adjust that. And the math of it's really easy. We want to maximize the amount of open shutter time. If our telescope is on the sky and the shutter is open, we are working. If our telescope has the shutter closed, we are not working. That's bad. We just optimize this number right here. This was developed several years ago, and we saw our efficiencies. I didn't include the graph because we've had this for a long time and the data is very old. We went from about 50% shutter to open time to greater than 85% open shutter time, because we were spending so much time selecting targets. And if we had, well, let me just show you. This is what the queue actually looks like. It's just a long list of targets. This one right here, same object. We're just going to sit on it and take exposure after exposure after exposure. This object here in the orange, though, we can expose, but we need to wait for a while before our next exposure to let it move across the sky enough to detect it. Well, we could just sit there and wait, or we could observe something else if there's enough time. The queue calculates that automatically and saves us a lot of effort. This has been a major improvement in CSS's efficiency. All right. Oops. Oh, no. Well, so it's supposed to show the stuff behind it first, but I guess it got flipped around. There we go. Anyways, I'll just explain it to you. So when we're doing follow-up, we're trying to find objects that are already known. So we have an idea of where they are and what their motion is, all right? But sometimes we'll try to follow up an object and it's just not there, or our normal image processing pipeline can't find it. Our observers will even look by eye at the images and blink them back and forth, like, see it? Do I see it? And sometimes they just can't find it. Okay, but what do? Do we know it's not in the field? Sometimes it's not, but sometimes it's because maybe the object got over stars in 2 out of the 3 exposures. Or maybe if we were tracking on the rate of motion of the object, because we try to observe objects with high uncertainty, maybe we didn't have the rate correct. So maybe we're not tracking on its exact rate, so the actual target is smeared out. Or maybe the object is just dimmer than we thought. Like I said, highly uncertain objects. That was the case with this right here. So this is blinking the follow-up images that we try to take of this object right here, right? And it should be in that circle, but I don't see it. It's not there. The reason you see a lot of long streaks of stars is because we're taking very short individual exposures and then trying to add them up. Basically, it's not there. So the person observing at the time looked at this and they tried to look around. They did a couple of other tricks and they said, I don't see it. We developed a way to use a technique called synthetic tracking. Now, synthetic tracking will try to blindly stack on a vector along an image. So it breaks this image up into little regions and it will blindly try to stack those up along different vectors. It's hugely computationally expensive, but it works. So if you would restack this along the rate, all 4 of these combined images, you would build up enough signal to detect the object, right? And we implemented this in a way that as soon as someone sees this and says, I didn't find it, let me reprocess it in a different way. Let me try to use synthetic tracking. Send it off to another computer, wait 10 or 15 minutes, get the notification, hey, it's ready, go inspect it, and it's right there. This saves us so much time because we would have had to retarget it. And this was a 20-second magnitude object we got with a 1-meter telescope. It took like an hour and a half. This saved that much time, being able to reprocess it. Notice other things. There's a lot of stars here. This was like in the Milky Way. So good candidate for synthetic tracking. But what makes it really special is we can do this in real time almost. So we can say within 10 or 15 minutes, do I need to reshoot it or did we actually get it? Another way that we save time, drive up our efficiencies. All right, on to the products, our discoveries. So we get here eventually. Took me a while to piece this together. Thank you to our data engineer for digging through the SQL to find these. This is a breakdown of CSS discoveries across the solar system, starting with the Atiras and going all the way out to distant objects, that'd be Centaurs, TNOs, everything far out there. We have found large percentages of the total populations of many of these families. We've been working for a long time, but we've also found really large percentages of Mars crossers, Hungarias, main belt, 30% of the main belt, and even further out, Hildas, Jupiter Trojans, found decent percentages of those over time. We in planetary defense focus on just this part right in here, the NEOs, but we've also contributed massively to our base knowledge of the small bodies in our solar system. And you can see it right here. Getting into the numbers a little bit more, That's almost 350,000 discoveries of minor planets, which is about a quarter of all known minor planets in the solar system. A quarter of the solar system. In terms of just sheer data points, that's 110,000 astrometric positions that we have sent in over 25 years. About a quarter of all observations. And this, I put this where you could just get a sense of what they look like. This is what we used to send in. We send in 80s now, but this is more readable. The object, the time, the RA, the deck, and the magnitude, and where it was. But, 110 million of those. All right, so that's our discoveries. What I really want y'all to take away is it's not just the NEOs or the asteroids or the astrometry. We also save every single image we've ever taken, right? And we have these on our computers up on the 5th floor, at least back into 2003 for the Schmidt and back until 2005 for the 60-inch telescope. 200 terabytes of image data up there, which feel free to use. It's there for you. So if you're not here, if it's hard for you to get in contact with me or anyone else on the team, we also upload to the PDS small bodies node daily our most recent data, right? So if you want to watch for it or grab anything, the PDS archive goes back until 2020 because our pipeline has changed, our cameras have changed, and PDS needs all of that documented, which that's a thing. If you're not a fan of digging through FTP folders, then PDS did start this nifty new searchable cutout program called Catch, where basically you say, I'm really interested in 67p. Go to Catch, enter that, and it only works for known small bodies. It will search through not just CSS, but also Spacewatch and Pan-STARRS and a couple of other surveys and give you every single image in a little cutout of when they observed that object. This would be incredible if you want to look at maybe there was activity, maybe there was an anomalous change in brightness at some point in time. This is a simple API-driven way to make investigations like that. Couple of details. I like to think of it, there's 2 timescales for our images. Okay, I said we take 4 images of the same field every night. So you have basically 4 images from our telescope separated by just a few minutes, right? But then we revisit the exact same field for these 2 telescopes about a month later. And for 703, just a day or 2 later, we'll revisit it. So if you need time series changes for a lot of different things in astronomy, this is a great archive to look at over months or over minutes. And if your object, the time variance is slow enough, you could take those 4 images and just stack them to build up even more signal to get dimmer objects. Also available, if you don't want to mess with images, but I like going back to the base images and reprocessing from there. We also have calibrated source images, calibrated source libraries for each image. If you don't want to mess with it, that's fine too. All right. Other products. Work that has used CSS data in the past to give you an idea of the possibilities. The probably most straightforward is CSS data is used for population models in NEOs. Right. That's what we find. People make use of that for models of their populations, but not just NEOs, young asteroid thing. This one was Jupiter Trojans, because we've discovered a significant quantity of those, but also we redetect them over and over and over, right? So that can also give you a sense of negative observation, like, well, we're not seeing any, keep looking. AGNs, yeah. Some folks have dug back through our archive, identified their own transients, and found active galactic nuclei in our data. Right? Gravity waves. I'm really proud of this one. This is an ongoing active collaboration. So, this is with the LIGO instrument. It will send out an alert. It's like, hey, we detected a possible gravity wave in this region. And it's fairly wide uncertainty region, but we have wide field telescopes, which we can reschedule right then. If they say, hey, we got a possible gravity wave event, they send an email, it reconfigures our queue to go and observe those fields. And that's fine because we can still find NEOs in those fields. It doesn't hurt us that much, and it can really help them. This is a perfect kind of collaboration. If you have a astronomical transient with high levels of positional uncertainty, we can work something out. Anyways, also binary star systems, we identify lots of transients, and especially if you look over time, you can see many of them in our data. And I have to mention supernova. We used to send our data just directly to Caltech, to the Catalina real-time transient search. They were the leading discoverer of supernovas for years and years and years and years and years. Just because we keep imaging the same sky over and over, and it's like, oh, that changed. Yeah, that's supernova. Send it in. It's great for that. And many more that I didn't have any more space. Right. So that's what has been done by others with our work. I also wanted to talk briefly about work that we have planned for the future, starting with characterization of small and close NEOs. So when we upgraded our main follow-up telescope, the 40-inch, and converted that to prime focus, we also included a 6-slot filter wheel. And the reason we did that was to start working on asteroid characterization, specifically on NEOs that come very close to Earth and are only in the sky bright enough for maybe one night before they're gone and too dim to observe. Or for imminent impactors, which are only observable until they impact. The reason we think our I-52 telescope is ideal for this is because we can retest that right then. As soon as an object is discovered, if it's discovered at 16.5 magnitude, which happens, we're right on it within minutes. It's not as good a data quality as, say, if you could, apply for time at IRTF, but then we don't have to write a proposal to attack every time we want to go and try to characterize something. So it's the ability to reschedule quickly this telescope that makes it useful for this particular case. 703 targeted survey for Atira asteroids. I'm constantly thinking of how to get our different survey telescopes to not compete with each other. And this is one area. 703 has an enormously wide field of view. And the Atira population is quite undersampled because of observational biases, right? Atiras can have a relatively slow, compared to something that's whipping by Earth, on-sky motion. So we could do longer exposures for these and make discoveries. The Schmidt you saw, we only do 14-second exposures because we're trying to cover a lot of sky and we sacrifice magnitude. Our plan is to do targeted long exposure Atira searches beginning and the end of the night, and then a more focused short exposure survey during the rest of the middle of the night. And we bounce up and down again. So that is something we're still working on. Common sharing of transients between major surveys. What do I mean? When we identify transients and we're trying to build tracklets, we have to have at least 3. Like no matter what, if we only have 2 points, we cannot say that that's the same object. Between any 2 points is a line, right? So we just don't know. So we may have 2 beautiful, perfect detections of an unknown asteroid, but if there's only 2, it's useless. It's invisible to us. But maybe another survey also caught some detections of this unknown transient. Well, could we combine our data on these transients to link them together? Used to be, no, that's kind of difficult. now, yeah, we hit it with a lot of computing power. We use a variation of the HelioLink linking algorithm, which if you've heard of LSST's work, that's similar. That's the same thing they use. We use a variation of that to be able to link transients across different topocentric sites on the Earth. It's possible. We're currently working with the Atlas survey to try to match our 703 with our 703 transients with their transients. It does work. We've actually been able to detect known objects with this method. I think this is a major area to push forward for, because in planetary defense, wouldn't you rather all the surveys work together? Right. Finally, enhanced citizen science projects. This is kind of my baby that I work on. But the Daily Minor Planet, our Zooniverse project, currently only hosts G96 nightly data. We could expand that fairly straightforwardly to the box survey and also to our Schmidt survey, just to give them more data. Surely there's more asteroids to be discovered there. It's really just a time consideration. Who wants to put in the work to do that? Also, some folks may remember that CSS had an outer solar system survey for a while. I think it's about time to restart that. Unfortunately, we're not funded to find TNOs because they're not a threat to the Earth. So that's just a wish. But maybe someone will want to work on that. Anyways, we're getting towards the end. A couple of closing thoughts. I really have to emphasize that our success as a program for over 25 years is due in no small part to the efforts of individuals working at night, all night, keeping on a night schedule. Our engineers who stay up really late into the night fixing the problems because things don't break during the day. Also, we were built from the beginning to be a human-centric survey. So we have resisted calls to automate, to use more machine learning to, to get past having to have people at the telescope actually reviewing the data. But we find that we can dig deeper into the noise with people, and that they are an asset. So we will continue with this methodology as long as we can. I hope you can see, because of the long list of projects and processes that I went over today, that we've been making continuous improvements as long as we have existed, and we still have many more to go. Our data products have been used all across astronomy and planetary science, and I hope now that you have an introduction to them that you can see uses for them as well. Finally, I didn't include that many pictures of our telescopes, but they are quite old. We really appreciate the work that Stewart puts into keeping these older instruments up and running, because we have made fantastic, productive use of them. And NASA really likes that because they're cheaper than building new ones. Right. I think, yeah, that's the end. I'd be really happy to take any questions, anything y'all want to discuss. Thank you.
Thank you. Are there questions?
Question. When you mentioned PDS as a tool to be able to enter in like 67p a comet or something and search through all the records, does that account for moving objects? Can you enter, it's moving over time, so it may go through multiple frames. Does it?
Right.
That's very computationally expensive. It does that?
It does that.
Okay.
Yeah, it is an impressive piece of software. Yeah. It currently only supports moving objects, so it has to have an ephemeris to rely on. I've been poking them every time I see GURBS, like, you have to make this work for a general or a deck and time coordinate.
That would be useful too.
Right. Yeah. Every time I see them, like, you got to work on, you got to work on this, you got to work on this.
That's impressive.
It is.
I'm surprised you didn't say much about, Starlink and that kind of contaminations. How big of an issue is that, or for your kind of survey?
Currently, right now, Starlink is not that big of a deal. But you noticed I talked about a specific wide field Atira search. Starlinks may prove to be an impediment to that, which is unfortunate. There may be large undiscovered Atiras. So that is a concern, particularly with that. When we're looking out towards opposition, satellites aren't that big a concern. But in that case, it likely will be. We're working on integrating a tool that can basically predict their motion, and we can try to schedule around them so we don't have them ruin fields, particularly with the Atira search. But TBD.
Slide is a great image for the question that I have, which is when you were discussing survey strategy, you said that a large part of it was designed to achieve complementarity amongst the different telescopes. And so I'm wondering if you were to try a design that was more targeted towards completeness, would that look wildly different? Or do you think that this is also achieving good completeness and complementarity at the same time?
If I had unlimited funds, then I would probably design a moderate aperture, moderate by today's standards, extremely wide field survey telescope. But I would also want multiple of them. Planetary defense works best and will achieve greater completion if we don't just have one really nice instrument, but if we have multiple instruments spread across the world, because we only sampled the northern hemisphere. And if it's cloudy here, we don't get any data that night. Well, there are definitely objects that if we miss them for a couple of nights due to their orbital configuration, we may not be able to discover them at all for years, decades. So I would rather have a more diffuse, I hate to say less capable, but I'd rather have more instruments working on it than one perfect ideal instrument with incredible follow-up support.
All right. Anybody else?
This is not a real question. I can just shout. How do we visit if we want to?
I am in 501A. Drop by if I'm in there, and we will schedule a time for you to come visit the telescopes. I always tell folks, we work at the behest of NASA. This is publicly funded, and you should see what you pay for. Absolutely.
So you have 5 telescopes running, and it's purposely a manual process at some level. How many people do you have working a night?
If all of these telescopes are running, we will have 4 observers. And that's an interesting question. We like to dedicate a single person per task. So one person running a single survey telescope works well. 2 people or one person running 2 survey telescopes, that's a lot. But we have 2 follow-up telescopes. I don't know why I'm pointing. We have these 2 follow-up telescopes. I'm of the opinion, and the rest of the team agrees, it's not just me, because follow-up is so strategic. You're constantly evaluating targets and thinking and recalibrating, that it helps to have one person running those 2 telescopes. Because if not, these 2 operators would have to just constantly be talking and say, okay, I'm going to get this one, you get this one. I'm going to get this one, you get this one. I missed this one. Can you try this one? That doesn't work well. It helps to have just one person. If we had 3 follow-up telescopes, maybe that starts to break down. But yeah, 1 on survey, 1 on follow-up in general.
Anybody online with questions? You can either put it in the chat or just unmute yourself and ask.
Hey, great talk. I had a question about complementary, but you also talked about sharing tracklets. So if the telescopes are, I guess, not wanting to look at the same portion of the sky at the same time, then how often are you able to share tracklets with each other?
So we do have the ability in our planning software to look at the previous coverage of other large surveys like Pan-STARRS and Atlas and anyone else who reports their coverage to the Minor Planet Center. And back in the day, maybe 10 years ago, we would definitely consider, Pan-STARRS just looked up here. Let's look somewhere else. Let's look for fresh sky. But what we found is that our surveys are so different that it doesn't make much difference if one of us has reviewed an area and another survey goes right over the same area. We're that different in our sensitivities. So especially with Atlas, which has such an enormous field of view, they cover the night sky in basically a single night. Overlap is fine. It doesn't hurt us on our initial detectability. And then the sharing of transients to make common discoveries is just, those are just bonus discoveries.
All right. Any other questions? Going once, twice. All right. Thank you, Carson. Thank you, everybody, for coming.